The Wright brothers first took to the skies in 1903. At Kitty Hawk, the world witnessed the first sustained and controlled flight. 11 years later, the first commercial flight crossed Tampa Bay in about 20 minutes. And another 5 years later, we saw our first transatlantic flight. If you take this trajectory moving from proven concept to commercialization, laser fusion is somewhere between Kitty Hawk and Tampa Bay. There is a global race to realize the potential of laser fusion. It's safe, clean, and sustainable. We've already seen ignition. Now the question is, how do we get from Kitty Hawk to that transatlantic flight? Focused Energy is a German-American company working to unleash the next chapter of economic growth and innovation through the adoption of fusion power. It is now developing Europe's first pilot plant for laser fusion, converting a nuclear power plant in Biblis, Germany, into a fusion power plant. Thomas Forner, CEO and co-founder of Focused Energy, joined us to share details on this ambitious project and to talk about the different paths nations are taking towards laser fusion. That conversation is next.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more. Today's episode is also brought to you by American Elements, the world's leading manufacturer of engineered and advanced materials. With a catalog of over 35,000 products available in both industrial bulk and laboratory quantities. To learn more, visit AmericanElements.com. American Elements. Now invent.
From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Tom, thank you so much for joining us and giving us the time. And I want to dive right into it. Focused Energy is now developing Europe's first pilot plant for laser fusion. Tell me where we are now with this project and where things stand.
So far we always talked about fusion as a lab story. Now we are speaking really building a fusion campus and a power plant, and we've signed an agreement with RWE, the State of Hessian, and other industry players to build out the fusion campus in Biblis and the first fusion power plant. And the goal is to have it up and running in roughly 2035.
Wow, that's fantastic. And I was reading this, and now this is repurposing an old nuclear site for this power plant?
So, yes, you're totally right. So this is a former fission power plant site, and I think this is very unique in Germany because we have decided back in 2027 in Germany to get out of fission. So, and the unique situation is that you have sites available that are in pretty good shape still, but are shut down and in decommissioning.
So it sounds like a very kind of attractive proposal too, because you're not just, we need space, we need this. It's like recycling. We're taking this plant that's not being used and we're going to make something special with it.
Oh, that was the core idea, to see how can we speed up, how can we use a site that delivers everything that we need for fusion. And fission compared to fusion delivers a lot if it comes to the conventional parts of a power plant that we can still use. So it means part of the infrastructure, the buildings, they can be repurposed and used for building a fusion campus in Biblis.
That's great. And do you think we could see a trend for this? Maybe other nations with a defunct nuclear site saying, hey, you don't just have to bulldoze it, repurpose it. There's still function here.
Maybe it's still a bit early. I think this is very unique for where we are in Germany to really see we want to go back into nuclear, but nuclear in this not into fission but in fusion. And in this case, the decommissioning path of Biblis is exactly meeting our roadmap. So it's almost a perfect match, and that's why we really had a very in-depth look into it, how we can use it and how it can speed us up. And I think this is very unique. In the long term, I think you can roll it out. You should. I think we should globally reconsider all kinds of power plants to be reused and to create kind of a recycling power plants and at least part of it. And this could speed up approval timelines heavily once we start rolling out the fusion power plants.
So what you're saying to is it sounds like not every power plant will be equipped to just try and flip into, laser fusion.
Totally right. I think you really have to carefully look at it where it's positioned, what size it was. In this case, Biblis was a 2.6 gigawatt power plant. We are planning to build a first of a kind with roughly 1 gigawatt. So in this case, we can not only build the first power plant there, but also the whole fusion campus, which means all the test facilities that we need to ultimately build the power plant. And I think that's a very unique space.
That's great. Exciting to see how it develops. And looking back and talking about the evolution of laser fusion, it's been characterized by kind of like a timeline of advancements through the last 3 years with fusion ignition achieved. The growth trajectory or technology arc, so to speak, has really shifted somewhat. How far are we today realistically from laser fusion powering homes and businesses?
Let me give you an example. So when the Wright brothers had the first motorized flight, it was I think 12 seconds and 38 meters, but it proved the science, and that's where we are in laser fusion, at least in the approach that we are taking. So we have seen Lawrence Livermore, the National Ignition Facility, not only once demonstrating net energy gain, but meanwhile many times with increasing gain. The last gain was 4.13. This means we have understood the physics. We know what conditions we need to create fusion reactions. And this physics can now be brought from science to engineering. So very simplified, what we want to do right now, instead of doing it once a month, we want to do it 10 times a second. And that's mainly engineering.
Great. So it sounds like it's proven, and then it's the matter of commercializing and getting like a kind of steady running process that you can repeat.
Yeah, you want to have it durable. You want to have it maintainable. So everything that you need in the end to get from a science gain to an engineering gain to an economic gain is what we are working on. This is exactly reflected in our risk register, in our roadmap, and in the different test facilities that we want to build to demonstrate step by step with each milestone that we are able to do this.
I think Focused Energy's latest announcement really marks a moment for Europe as it works towards a new path to energy. But we're seeing other nations around the world with their own roadmap to laser fusion. The US is investing heavily in fusion now and talking about how AI can be utilized. And we've seen, Germany, a new fusion action plan. Tell me how Europe's plans kind of differ from that of the US or other nations kind of following their own roadmap to fusion.
So I think US was pretty far ahead when they announced this fusion program. I think it was roughly 3 years ago. And we as Focused Energy, we are part of this program. So we are one of the 8 awarded companies. I think it was a very solid approach because it's a milestone program that is favoring private-public partnerships. And from what I'm seeing, this was kind of a role model, how also other countries now look at it. So the main goal for each country is to bring fusion away from science to more engineering endeavors and from labs to industry. And I think in the US, it has worked quite well. I mean, still, we don't allocate enough money in neither in US nor in any other country. But the way the money is allocated is working really well. Like for us, we have delivered now our first 3 milestones for the DOE program. We just got eligible for the next phase. We are developing the next milestones, and at the same time, we had the opportunity to win awards in Germany as well. And the program we are speaking about in Germany is likely very similar to what we have seen in the US. To really have a milestone-based program away from the labs, with focus on private-public partnerships and industry to, on the one hand, build the first facilities that deliver the necessary milestones to prove that we are on the right way to a power plant. And second, and I think which is probably the most important part, is we are not just building startups, we are building a whole new industry, which means we have to ramp up a whole ecosystem. You have to bring in the industry. You have to, for laser fusion, like you have to mass produce laser glass. You have to mass produce large optics. You have to get, in terms of laser production, where lasers today in the high energy space are developed like satellites, we will have to produce them like cars. And that's where the big money needs to be invested. Not so much in the fusion startups. Fusion startups, we will profit from the upscaling industry, and that's what we advocate for.
Mhm. So talking about, building the kind of the economy of this whole system, and now if we place the race to commercialize laser fusion into a global context, what are more of the key themes or hallmarks of this dynamic, and kind of who are the players, and how do their plans to commercialize fusion differ?
I mean, the plans how to commercialize fusion, I think, rather differs from startup to startup. And so some of them want to build their own power plants, run their own power plants. Others just want to be part of the supply chain. Others, like us, so we are really focusing on the ignition mechanism and the fuel. So the way we are looking at it, to be able to scale, I mean, how many power plants can you build at the same time? Not so many. So what we want to do is we want to have partners and national ecosystems, and then work with different countries, different partners in local ecosystems to build up power plants, to roll out power plants. And the piece that we are providing is how you ignite the fuel, how you ignite this tiny pellet, and then we want to deliver the fuel in perpetuity. This is our core IP, the fuel, and how to ignite it. And that's going to be needed for each and any power plant. And that's our way to commercialize. So in the end, simplified, we don't want to become a company that runs a power plant. We want to become the next Saudi Aramco.
Gotcha. Excellent. And when we think about all the powers pushing, fusion energy, we can see it's growing, and like we're talking about too. Certainly, always more room for more funds for everything we're trying to get done. Um, when you talk to someone who may not be as knowledgeable on it, how do you kind of characterize the benefits for fusion technology as a whole? For the nascent, the growing fusion industry. How do you, if someone is ill informed on fusion and says, well, does this create waste? Does this do this? How do you, tell them the benefits of what you guys are working on?
First, I would always say um, fusion is the ultimate energy source. It's powering the universe, and it's the last energy source that we have not unveiled yet. And it's the only one that can decouple energy production from resource consumption. And why? Because the amount of fuel that we need is neglectable. So to run a gigawatt power plant, we need 3 Coke bins of fuel per day. And that's it. So it means it is easy to run. You can place it anywhere you want. It's inherently safe. That's the other piece, especially in laser fusion. Because if you imagine you shoot in this tiny pellet into the chamber, and you want to hit it with the laser from all sides. If something happens, the first thing that is not working, the laser would not hit the target anymore. And it just falls through. Nothing happens. And if nothing happens, there's no exhaustive heat. There's no chain reaction. There is no nothing that could really happen. And even the tritium, which is the radioactive piece in this part in this whole system, is either bound in metal or bound in the targets. So nothing can disappear. And we have conducted some studies about this safety aspect, and this will differentiate fusion a lot from almost any other energy source. Next, what I would always argue is what I said before. We have seen that the physics works on Earth. We have seen it in the universe many times that it works. For us on Earth to utilize it, we have seen it at Lawrence Livermore. And now it's about engineering it. And the reason why we can engineer it right now, because the underlying technologies have improved the last 5 to 10 years. Means high energy lasers, diodes. So diode production, which is very comparable to semiconductor production. The cost comes down. And I think one really, really important thing is AI. And AI not only as a future off-taker of the energy, but an enabler for us. Because if you want, fusion is probably the ultimate problem of a system of systems, where you optimize so many different parameters at the same time. We always have to decide in between trade-offs. That you need very sophisticated simulation and AI that helps you to run these analysis and these decisions in real time. And the other important step is, or important piece is, that we still miss a lot of data. We have some data from Livermore that we can match with simulation tools, where we know the fusion conditions, but there are still many spaces where we need predictive analysis, and AI helps there as well. So it means AI is definitely something that can speed us up, and AI really in an understanding of rather coming from native AI and add science to it, than the other way around. And that really accelerates us, and that decreases our risks heavily and enables us to build the first prototype power plant in the 30s.
That's fantastic, and it's nice to hear that too, because people, when you hear different things of different energy, if you're not in the industry, you may think of the worst story you heard, but to hear about the safety of it, and I think something that had people concerned with nuclear aspect was fuel and things of those. What happens with that when it's done? But I want to talk now about Pearl, because I was very interested to read more about this. This is Focused Energy's fusion fuel derived from seawater and lithium. And I read too that Pearl can increase energy output 30 times compared to NIF. So tell me, how does this work? And I mean, making use of seawater seems so, you're recycling the power plant, we're using seawater. It's like, what a great eco-friendly system.
Oh, yeah. So the main part of the fuel is so we use DT as a fuel. Deuterium and tritium, both are hydrogen isotopes. Deuterium is in seawater. It's roughly every 3,000 molecule in seawater is deuterium. So you can filter it and you can use it. Tritium is the other part that you need for as a fuel, and both deuterium and tritium react in a fusion reaction, form helium, and release a neutron. And that's how the energy is produced. So the neutron carries the most part of the energy, and detonates it in the inner part of the chamber, so in the first wall, and that's in form of heat. That's the basic reaction. So coming now to our Pearl, it's very comparable to what NIF has in their targets. So this Pearl in the inside of the whole realm is very similar to what we are doing. But we have developed ways to optimize the sphere. We have ways developed to optimize how you can fill this target. How you can cool it down. So all these steps they have been done already, but not in a way that you could produce 1 million per day. And that's what you need if you want to shoot at 10 hertz, 10 times a second. This means you almost need 1 million targets per day. And you want to do this on site at each power plant. So you have to have a system that allows you to produce almost perfect targets with self-organizing structures, with many ideas that allow you to do this. So what we have done, and Marcus has done this already for the last 20 years, we have built a target lab. And we took over at the very beginning of the company the target lab from University of Darmstadt and all the IP that Marcus, my co-founder, had generated the last 20 years. Meanwhile, we have moved this target lab from 200 square meters to almost 2,000 square meters. And that's where we have all the metrology, the microscopes, the CTs, also micromilling machines, cryogenic machines. So everything that allows us to do R&D on the one hand and produce mass manufacturing methods on the other hand. And this is the core IP. So it always relates to the laser because this is what I meant with the trade-offs. So you have to have the right laser, the right bandwidth, the right beam shape, the right pulse to ignite the target. And if you want to improve this mechanism, you can either improve on the target side or on the laser side, or both. And that's what our team, so mainly our scientists that we hired from Livermore and from other labs, are doing. They are optimizing this process, which we would call our point design. And this is exactly how you get to higher science gains. So if you find a mechanism that allows you to compress a larger target, to compress more fuel, then you can increase your gain. And that's and in our plan, how we get from a gain of 4 from Livermore to a gain that allows us to demonstrate an engineering gain and later on an economic gain. We have 2 core things. So the one is go from indirect drive to direct drive. This allows us to increase the target, to increase the fuel in the target, and to get from a gain of 4 to a gain of 50, 60, 70. And the other piece is to get to improve the laser, where the NIF laser today has a wall plug efficiency of 0.5%. We know that modern diode pumped lasers can get up to a wall plug efficiency of between 10 and 20%. Both combined brings us to engineering gain, brings us to economic gain. And that's the core of our engineering challenges.
Right. And, speaking of challenges, I know we talked about, mass producing the components that are needed to build laser fusion systems. Are there any other kind of core bottlenecks that are we're still working to kind of overcome to really push this forward?
Oh, yes. I think there's a whole system of different challenges that we all tackle at the same time. But nice thing in laser fusion is we have a very modular approach. So we can develop the different technologies separate from each other and then integrate them. And this allows us, for example, to work on the laser separate from the chamber, separate from the target, separate from the injector. And on all ends, we build right now test facilities. So we already have the lab where we produce the target. We are right now about to develop a target shooter where we can accelerate the target to the right speed, where we can build the right tools to track the target and then hit the target and adjust the lasers. We develop the laser separate together with partners, and so we have a large laser team, which we hired, where we hired some of the most experienced high energy laser people that have been working on this for the last 1 or 2 decades, and we combine this with partners like Trump Laser Systems or Amplitude, where we have people who have knowledge in productizing lasers, making them maintainable, making them durable. So bringing it really from 0 to 1 in prototyping, and then from 1 to industrialized scale for building power plants. The one of really important remaining pieces is still first wall and tritium breeding blanket, where we also collaborate with other companies, other fusion companies, and other labs. And where we still have to define the final material that we are going to use for first wall, and also how we will set up the breeding blanket. And so this is also a separate piece that we are working on. The bottlenecks are really, I would say the biggest bottleneck is the availability and affordability of the lasers within 10 years. Because it's not only about that they technically do what they shall do, but they have to be affordable so that they can build test facilities and a prototype power plant. So that's probably I would say the biggest challenge, and it's a industrial challenge. It's a bit comparable with what we have seen in the battery development, like 20 years ago, when Tesla started to wrap laptop batteries to outfit the first prototype cars. I think we're a bit more advanced like this, but we still have to scale it up. And of course, let me not forget one thing, systems integration. System integration, control systems, the whole software part behind is also a challenging piece.
Gotcha. Well, it's certainly exciting to see the progress being made. And I'm going to ask you the impossible question I like to ask on some of these things is, where do you see the future of this, immediately and maybe 10 years from now? I know we talked about when, the plant is expected to open, but what do you see as the future for laser fusion, both in Germany, Europe, and globally?
So first of all, I would say midterm, we will see that we build test facilities and hit our milestones. On the maybe in the ecosystem, you will see companies that hit the milestones and companies that fail, companies that disappear, companies that pivot, and maybe companies that merge with each other. So that's I would say what you typically see in the early but accelerating phases of startup ecosystems. In the next 5 to 10 years, there will be a heavy selection. So if you, on a global scale, you will not 53 or 54 startups will survive. You will only have a few that will really seriously build power plants. And the selection we will see in the next 5 to 10 years. So it will be selected down and really, again, driven by milestones and how we can hit your milestones. Beyond that, I hope we will see during this phase also ignition in magnetic fusion. So I really hope that many approaches will succeed. My personal opinion is that only those today that are really peer-reviewed and have a solid scientific base can be successful. All others not. And within 10 years, we ideally see the first prototype power plants coming to the grid. And then, I think still today, it's hard to judge which approach is the commercially most interesting one. I think there are good arguments for laser fusion, but we don't know it other than simulations. And we will see this in the next 10 to 15 years when we start rolling out power plants. And ultimately, we will know it once we are in the 40s, mid of the 40s. This will then be the next generation of power plants where we really see global scale development of fusion.
Very exciting. Tom, thank you so much for giving us the time, and please keep us updated with what Focused Energy gets up to.
Thank you. It was a pleasure.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.